Hello everyone, a very good evening to all. Are you able to see the screen?
Good evening, sir. Yes.
Yes, Ramesh, thank you. So let us begin the session. So I welcome you in this live tutorial session number 4. And first, before we begin to solve the problem for assignment 4, so in previous session, someone has having doubts regarding this series connection of PV cell and why we do using of bypass diode through the modules, not through this a single PV cell. So we will just have quickly revise from this big tools. So coming to this connection of series connection of two identical cells, it is very easy. Means like if two sources are connected in series, then current cannot be changed. So and both are identical. So this short circuit current will be equal to ISC1 equal to ISC2. And this equivalent circuit voltage will be summation of this single open circuit voltage plus a single open circuit voltage for PV cell 1 and the open circuit voltage for PV cell 2. So this is the configuration for two identical cells. Now the problem comes
Actually,
when
sir, I think. Sorry, sir. Sorry for interruption.
yes,
I think question was in one module. There are several cells, like 72 cells
yes,
nowadays in one module. So each module. Uh, each each module having diode. Either we use only one diode in one module. Yeah.
yeah.
my
So
question
that's
my question my question is we are using diode throughout the
module, not the for a single cell.
throughout the cell. Yeah, only module, only one diode using in one module.
So that's we are coming to your question. So I am giving the quick recap. Means like we should start from the identical cells. So I got your question. What you are asking means why we connect not through a single cell, why we connect through a series of, why we connect through a module that is having a series connection of several cells. So that is the practical scenario. Means like even if the manufacturer provided us this PV area module, then it does not having all the cells having similar IV characteristics. So they are working on their operating point based on the load. So now if we are having non-identical cells in series, then again this equivalent open circuit voltage will be summation of this summation of the each open circuit voltage of each PV cell. Now how we will find this equivalent short circuit current? So this equivalent short circuit current is basically determined from the BK cell. That cell either goes on shaded region or it may be some having defects. So the short circuit current is determined by this BK cell. Now this if we say this cell 1 and cell 2 characteristics, from this characteristics we can say that within a certain region of IV characteristics, this means cell 1 and cell 2 both are operating as a source, and in the certain region, this cell 2, those cells that are in shaded region or defected, they went into this. They are acting as a sink. So what will be the worst situation? Like if we are increasing the load, like if we are increasing the load, then we are reducing this resistance. In that case, if we are again and again reducing the resistance, then we go beyond this curve here, this shown over here, this shaded region. If we go beyond this curve, like so, this PV cell 2, like this is shaded cell. So this will act as a sink. So till here, this point, that this line, both are acting as source, and beyond this point, this PV cell 1 acting as a source and PV cell 2 acting as a sink. Means it is dissipating power. Now the worst situation comes when this resistance value will going to be 0, or we can say that we have increased the load. We have increased the infinite load, like at which the current demand is maximum. So in that case, this PV cell 2 is dissipating the maximum amount of power. So let us see this case. Like we generally tell this term as hotspot generation. So let us make the ideal PV module, equivalent circuit of ideal PV module. So first we are taking two cells are connected in series. And here I am taking the brushed situations. In that case, the cell having the weakest cell that went into shaded region or that may be defective. In that case, that cell will be acting as a sink and dissipating the maximum amount of power. So we are taking the short circuit condition. So in short circuit condition, this R0 will be 0 and this load line will be infinity. This first is PV cell 1 and the second one is PV cell 2 and this is shaded cell. And let us take the open circuit voltage for PV cell 1 VOC1 and short circuit current is ISC1, and for PV cell 2 VOC2 and ISC2. Since this one is shaded cell, so this ISC2 taking as less than ISC1. So we know that if two identical cells are connected in series configuration, then we can say that in some portion of I am extracting the words from the lecture of this course. In some portion of IV characteristic of series combination, this PV cell 2 acts as a sink So let us take the worst situation in which we have taken the short circuit condition. Let's take the means we have short circuit case. This R not equal to 0. So we will find first, like if we are having n number of PV cells and one cell is defective or in seeded region. So what is the amount of power they are dissipating? First, we will make the n number of PV cells connected. Let us denote by this symbol of PV cell. So let us consider this PV cell 1, PV cell n that is in shaded region. And other cell 1, cell 2, this is PV cell 1 and the last one is PV cell n and that is in shaded region. And let us consider this voltage across each cell is VT. And now we are considering this voltage across the shaded region is V shaded. Now we can say that this voltage across the shaded cell is minus, sorry, so this one will be minus of n minus 1 VT. So this comes from this KVL. So we can say that dissipated power across this shaded cell will be n minus 1 into VT into I. right? So how we can reduce this dissipated power? So for that we are using the bypass diode, as the sir has discussed in the lecture. Now we will see this how means how much this reduction in dissipated power if we connect the diode, bypass diode across this seeded cell. So let us connect this bypass diode. So, and for silicon diode, this cut-in voltage, for silicon diode, this cut-in voltage across this bypass diode, if this bypass diode is made of silicon, it is generally 0.6 to 0.7 volt, right? And if you are using Schottky diode, that is more, that is having cut-in voltage lesser than this silicon diode. So in that case, it will be 0.3 to 0.5 volt. So like if we are using this junction diode or bypass diode across the seeded cell, then in that case we can say that this like voltage across this protected diode will be 0 minus 0.6 volt, and now the dissipated power will be 0.6 into I. So here we can say that in the previous case, when we are not using the bypass diode, this dissipated power is having a large number, means like this n minus 1 into Vt. So this quantity is much greater than 0.6 volt. So this dissipated power across the seeded cell has been significantly reduced. Now the question comes that is this economical to use this bypass diode across each PV cell? So the answer is no, because this bypass diode will work only if it is having cut-in voltage at least 1/10 of the cut-in voltage of each PV cell. This bypass diode will work only if it is having a cut-in voltage at least 1/10 of the cut-in voltage of PV cell. Why this so? Can anyone tell? Means this is the reason. This makes the if you make the bypass diode that is having cut-in voltage value is 1/10 of the cut-in voltage PV cell. If you manufacture this type of bypass diode, it will cost expense. It will having very high cost. So we don't prefer this bypass diode across each PV cell. Can anyone tell the answer? Means why we are having this should be the condition, means the bypass dash be work only if it is having cut-in voltage at least 1/10 of the cut-in voltage of each PV cell. So if you got the answer, just tell me. Otherwise, just to remember this point, that this bypass diode is working only if this cut-in voltage having at least 1/10 of the cut-in voltage of each cell. To make that type of bypass diode, it will cost much high. So the solution is that we can say that this makes this makes bypass diode expensive to be put bypass diode across the cluster of cells. Across the cluster of PV cells. In spite of putting bypass diode across each cell, we put this bypass diode across the cluster of cell so that this condition is satisfied. Means this, if you find this cut-in voltage of bypass diode should be 1/10 of the in voltage of module, then it is satisfied. So we are putting the bypass diode across the cluster of PV cells, not through a single PV cell. And in the designing of this bypass diode, some things like we should some conditions also, like this forward current for bypass diodes to be more than 1.25 times of short circuit condition for the group of cells. Means so the means 1.25 times of the short circuit current for this cluster of PV cell. That is the first condition. And this blocking capability, that is breakdown voltage of bypass diode, should be 2 times of the open circuit voltage of the PV module across which this bypass diode is put. So this is not a discussion for this our course, but for designing of this bypass diode, we are keeping two things in mind, like this forward current, means current rating for this bypass diode should be 1.25 times of short circuit current of the cluster of module, means of this cluster of PV cell, or you can say module. And this breakdown voltage should be 2 times this open circuit voltage of the module or cluster of PV cells. Any doubt, anything you want to say?
No, sir. It's clear now. Uh, this
Yeah.
is just that you confirm that we are not using diode across the cell. We are using now diode across the module, not the cell,
Yeah,
due to
across the
the expensive.
yeah, due to more expensive, we cannot design this type of diode having this cut-in voltage is 1/10 of this cut-in voltage of PV cell. And if we put across the module, then it is easily satisfied. That is the advantage. And other further advantage are also, but that has not discussed in the class. So let us come to this current assignment. Assignment number 4. So let us see first the means in the previous session we have seen the how we can find the energy incident for a horizontal flat plate. Now in this current session we are going to see the atmospheric effect on the solar insolation and this energy incident on the tilted flat plate with atmospheric effects. So in this slide, you can see that in the left hand side, we are having this solar insolation for horizon plane, means for the solar cells that are put on this horizon plane. But if you put the solar cell on having some tilt angle, and tilt angle is denoted by beta, then what are the things are going to change? Like if we see this solar insolation that is normal to this horizon plane, the equation is del cos omega cos phi plus L sin phi. And this del is declination angle, omega is our angle, phi is the latitude. So this is for the PV model are putting in this horizon plane. So if we find this solar insolation that is normal to the PV cell, the equation comes like that. Now if we are going to tilt this our PV cells in the base of equator, like we are tilting this solar cell such that this collector tries to face the equator, and you are given with this tilt angle, then how we can find this solar insolation, that is, and what are the factors that are going to be affected in this solar insolation normal to the uh, solar module. So this del is time of year, this will be unaffected, and this omega, this time of day, it is also unaffected. The affected thing is this latitude phi. And what is the new latitude? So if you see here, so this is phi, and if we find this angle, this will come out as phi minus beta. So you have to just put phi minus beta in the place of phi for the new equation. And then we get the solar insolation on a tilted flat plate. So this is a combined axis for this uh, for this tilted solar PV cell. So this plot on the right hand side, this is made on the merged coordinate axis system, and it consists both local centric coordinate system and earth centric coordinate system. So it is easy to remember this solar insolation for a tilted flat plate if you are knowing this solar insolation on the horizontal flat plate. The only thing you have to change that is latitude. So in the place of phi, you have to put phi minus beta because this angle is going to be changed. Now coming to this daily energy incident on a tilted flat plate. So we are knowing the expression of daily energy incident on a horizontal flat plate, that is given by this equation: 24 L upon pi cos del sin omega SR plus omega SR sin phi sin del. Now we have to write the daily energy incident for a tilted flat plate. So again, what are things you have to change? So the things you have to change, that this latitude angle, and delta is the declination angle that depends on the time of year. So it is going to unaffected, and this sunrise hour angle is also affected. So this you have to change this sunrise hour angle with this omega SRT. And how you can find omega SRT, that is shown over here. So this sunrise hour angle with respect to horizon plane is given by this cos inverse minus tan phi tan del, and for a tilted plane, that is omega SR beta, that is given by cos inverse minus tan phi minus beta tan del. So you have to take the minimum of omega SR and omega SR beta. So that will give omega SRT. So we have to take the minimum of omega SR and omega SRB beta, that is omega SRT. So equivalent sunrise angle for this daily energy incident on a tilted flat plate. So it is quite easy to remember if you are knowing the daily energy incident for a horizontal flat plate, then you can also find for the tilted flat plate. Now coming to the one important concept, that is air mass. And in this session, there are two problems based on the air mass. So what is air mass? So this air mass coefficient defines the direct optical path length to the insulation through the atmosphere. And this is expressed relative to the zenith path length, which is normal to the horizon plane at sea level. And it is denoted by AML. So it is written like AM0, AM1, AM1.5. And how you can find this L? L is just L is equal to 1 upon cos theta z, or you can say sec theta z. So this is the zenith angle theta z. So for this figure shown over here, how you can find the air mass? The air mass will be equal to pi upon x. If you take this cos theta z, 1 upon cos theta z, it will come as pi upon x. And if it is written AM0, that means there is no atmosphere present. So in some cases, if you are shown in like in many websites, they have done the they have they were written like AM0, means you have to understand that they have not considered any atmosphere. And AM1, that means the sun is along the zenith axis. In that case, theta z will be 0 and cos theta z will be 1. And the standard air mass be considered AM 1.5. In that case, theta z comes as 48.2 degree. And if you want to go more on this air mass, you can refer this air mass description from this pveducation.org. This is a very good website for basic understanding of the solar energy. So from here, I have taken the figures and the concepts, and you can also find this directly by putting the data, means like sun position, where is the sun position, how from by putting this theta you can get the air mass. Now how we can find the air mass? How we can find the air mass at place other than sea level? So this expression is for this air mass at the sea level. So to find mass at the place that having a height, some height like at some mountains or some hills, so that we have taken AML star. So L star equal to P upon P naught into L. So this expression will help you to find the air mass other than the sea level. Now in some problems they may ask you to find air mass if an object is given and its shadow is given. So in that case, the expression for this air mass for object and shadow will be like this. This air mass is the length of the hypotenuse divided by the object height. So you can also write air mass is the hypotenuse length. So hypotenuse length will be object height square plus shadow height square upon object height. So if you do simplify this expression, you will get this air mass for object and its shadow. Now coming to this another point, that is daily energy incident on a tilted surface with atmospheric effect. So whatever the irradiance coming from the sun, some irradiance is like they are coming directly on this PU panel and some are getting reflected. So that is shown over here, and that we call albedo, and some irradiation are diffuse irradiation, like that here is represented by this coming from this cloud. So you can say this. Yes, anyone want to say something? Ramesh, you. So we are quickly revising. Yes.
What is the albedo, sir?
Albedo is term that we named for this reflected solar irradiation. So it is a term that is for this reflected solar radiation, ground's reflected solar irradiation. So this is not that much complex. So you can say that this atmospheric solar energy incident is equal to direct energy incident plus diffused energy incident plus reflected energy incident. Now how we can find from the mathematical expression, how we can find this HAD from the mathematical expression. So for that we are defining some factors. One is the tilt factor. One is this tilt factor RD, and another one is this clearness index KT. So tilt factor you can define with defined for both atmospheric effects and without atmospheric effects. So tilt factor is like what is it is the ratio of daily energy for the tilted surface upon the horizontal surface. So if you are not considering atmospheric effects, then it will be HOT upon HO. So H0 is the daily energy incident on a horizontal surface that we have seen in the previous session, and HOT is denoting the tilted surface, tilted PV panel. So HOT upon H0 will give the tilt factor RD, where we have not considered any atmospheric effects. And the expression for this RD will be cos phi minus beta upon cos phi into sin omega SRT minus omega SRT into cos omega SRT minus sin omega SR minus omega SR cos omega SR. So you can refer the lecture. And now if you are adding tilt factor with atmospheric effect, now in that case, in place of H naught, you have to place HA, because you are considering the atmospheric effect. So it is the ratio of daily energy incident on tilted surface with atmospheric effects upon daily energy incident on horizontal surface with atmospheric effects. So both value will come as equal, because in one case we have considered atmospheric effects and in other case we have considered no atmospheric effects. So if you cut this atmospheric effects, then it will come this RD equal to H naught T upon H naught. So we will use this in the further relation. So just remember this tilt factor. Tilt factor is nothing, means daily energy incident on tilted surface with respect to horizontal surface. And you have to also keep in mind this relation. Now coming to this clearness index. Clearness index, this clearness index is the daily energy incident on, daily energy incident on horizontal surface with atmospheric effects upon daily energy incident on horizontal surface without the atmospheric effect. So it is HA upon H naught. And so I've written it twice. I think there is no need of it. So we know this RD is equal to HAT upon HA. So HAT can be written as RD into HA. So if you put HA from this KT relation, so you will get RD into KT into H naught. So this is one of the important relation. With the help of this, we can find the daily energy incident on horizontal surface on a tilted surface with atmospheric effects. So with the help of clearness index and tilt factor, we can find the daily energy incident on tilted surface with the atmospheric effects. So you can write this HAT is daily energy incident on P is denoting tilted surface and A is denoting with atmospheric effect. Daily energy incident on tilted surface with atmospheric effect. So this is the all the practical scenarios are considered, like tilting of these PV panels and the atmospheric effects. So with this relation, we can find the daily energy incident on tilted surface with atmospheric effects. Now we can simplify more this. So how we can write HAT? So HAT can be written as HA into RD minus HD into RD plus HD into 1 plus cos beta upon 2 plus HA rho 1 minus cos beta upon 2. So this first term is denoting direct due to direct irradiation, and the second term is reduced is termed as diffuse irradiation, and the third term is denoted as reflected irradiation. It's coming from the reflected irradiation. Now, if we take common HA, then it will be written like this. Now, taking common from HA from all the terms, then we can write HA equal to HA gamma T. And this gamma T is overall tilt factor. And the curve fit relation for this HD on HA, we can write it as 1 minus 1.13 kT. So this is curve fit relation. We need to use to find SD if we are knowing this kT, and then rho is denoting this reflection coefficient that vary from 0.1 to 0.7. Now coming to this steps to estimate HAT. So these are steps, and that we will use in the solving problem. There no need to discuss it further. So till here, any doubt? रमेश, मेयर केगर, चन्ना, जानवी, नीरज कुमार, रजनीकांत, प्रभाकर, विकास मिश्र. So from now onwards, I am showing one problem you here. You can type your answer in chat box, or you can tell also. So just solve parallelly with me. Let us come to the first problem. The first problem is that a solar collector is tilted at an angle of 20 degree with respect to horizon plane at some locality. So this tilt angle is given as 20 degree. So what are the things given? So tilt angle beta is given as 20 degree. The latitude angle of the same locality is given as 30 degree north. The latitude is given as 30 degree north. So 30 degree north, that means we have to consider positive or negative. Can anyone tell?
Positive.
Yes. Yes, Ramesh, it is positive 30 degree plus 30 degree. And you have to find this what is the effective incident energy in kilowatt hour per meter square per day collected by the solar collector on 20th May of a non-leap year. So the date is given and it is a non-leap year. So from here you can find the n value. So n will be 31 for January, then 28 for February, March 31, April 30, and May will be 20. So it is coming as 140. So we have to not consider any atmospheric effects, only this tilt surface. So we have to find the HOT, H naught T. So H naught T equal to what? First, first we will write the expression of H naught T, and then we can get the each expression. So H naught P equal to 24 L upon pi into cos del cos phi minus beta sin omega SRT plus omega SRT sin del sin phi minus beta. So we have to find the H naught T from this expression. So in that expression, we are not knowing the L value, we are not knowing the del value, declination angle. We are knowing this phi, beta, and we are have to find this omega SRT. So we will find each one step by step, and then we will put all the things in this expression. So let us first find the L value. So L value is solar constant LSC into 1 plus 0.033 cos 360 n upon 365. So LSC is given 1.37 kilowatt per meter square into 1 plus 0.033 cos 360 n. So n is given as 140 upon 365. So if you do simplification, you will get 1.4147 kilowatt per meter square. So keep in just be cautious here. This inside the term of cos, it is in radian. So set your calculator in radian to find this value. Now the next term we will find the del. So we know the del declination angle expression. Declination angle expression is 23.45 sine 2 pi into n minus 80 upon 365. So 23.45 sine 2 pi, n is 140. So you will get del as 20.138 degree, or in radian you can write 0.3515 radian. So we know this L and del. Now only one thing is unknown, that is omega SRT. For finding omega SRT, we will find omega SR first and omega SR beta. So let us find omega SR. Omega SR is cos inverse minus tan phi tan del. So it will be cos inverse minus phi is plus 30 degree and tan del is 20.138 degree. So you will get cos inverse minus 0.2117. So 102.1 2 to 3 degree, or in radian it is 1.784 radian. Now we can find omega SR beta. Omega SR beta is, that is solar hour angle with respect to tilt surface. So in the place of phi, we will put phi minus beta into tan del. So it is cos inverse minus tan phi minus beta will be 10 degree, and del is 20.138 degree. So it will give you 93.71 degree, or in radian it will give you 1.6355 radian. So we know that omega SRT is minimum of omega SR and omega SR beta. So minimum is this omega SR beta. So this will be 93.71 degree or 1.6355 radian. Therefore, we have to just put all these values here in H not P. So 24 into L we have found 1.4147 upon pi. This cos del is, so here we are putting our calculator in radian. So we are putting all the values in radian. So cos del is cos 0.35147 and cos pi minus beta 0.5236 minus 0.35, and then sin omega SRT. Omega SRT is 1.6355 plus omega SRT is 1.6355, and then sin del 0.35147, and then sin phi minus beta 0.5236 minus 0.35. So just we have to do simplification. So you will get 24.1.4147 upon pi into, it will come 0.9228 plus 0.09726. So finally we will get H not equal to 11.02 kilowatt hour per meter square per day. Are anyone getting this answer? Please do the simplification and calculation. If you don't do right now, then you may struck in the exam also. In this type of problems, you don't have to put any mind, just you have to know the expression. You know the method how to solve the problem. And just practice some problems, so you will don't fear in the exam also. And this will be helpful in your current assignment also, assignment number 4. Now the second problem comes here that in question 1, what is the value of estimated hour angle in degrees of the day for the calculation of effective incident energy received by the solar collector if the tilt angle is changed from 20 degree to minus 20 degree. So you have to find the estimated hour angle degrees, hour angle in degrees of the day. So sorry. So you have to find the estimated hour angle in degrees for the day. So in the last problem, this tilt angle is given as 20. Now tilt angle is given as minus 20. So what is the length of day in degrees you have to tell, because they are telling to find the hour angle for the day. So here we'll find for beta equal to minus 20. In the last problem we have found for beta equal to 20. So for beta equal to 20 minus 20. So let us find this omega SR. Omega SR is cos inverse minus tan phi tan del. So there is no tilt angle comes in this expression. So it will be same as the previous problem. Omega SR will be 102.223 degree, or so here we are keeping in degree only. And then omega SR beta will be cos inverse minus tan phi minus beta into tan del. So it is cos inverse phi is given as 30 degree. So it will be 30 plus 20, and then tan del is 20.138 degree. So cos inverse minus 0.437. So it will be coming as 115.91. So in that case, estimated hour angle, that effective hour angle will be minimum of omega SR and omega SR beta. So omega SRT will be minimum of omega SR beta. So here in the last problem, omega SR beta is coming as lower value than omega SR. Now in this problem, if the tilt angle is changed from 20 degree to minus 20 degree, this omega SR is coming minimum. So you have to take 102.223 degree. So how we can find the length of day, or you can find the hour angle of the day. So this length of day will be twice of sunrise hour angle 2 into omega SRT. So it is 2 into 102 degree. So it will be 204 degree. 204 degree the answer. Did anyone got this answer?
Yes, sir.
Okay, Salini, you also put your answer in chat box so that other can also get motivated. Now coming to the next problem. A solar panel is placed on a rooftop of a building if it is tilted at an angle of 25 degree with respect to the horizon plane of the local coordinate system. So what are things given here? Given are this tilt angle. Beta is 25 degree. Now the ratio of incident energy at the tilted horizon plane to the incident energy at the horizon plane of local coordinate system is 0.95. So what is the ratio given? So it is given H naught T so it is given H naught T upon H naught. So H naught T upon H naught is given as 0.95. So what we call this H naught T upon H naught? We call it as RD. This is tilt factor. Tilt factor RD upon tilt factor RD, that is H naught upon H naught, is given. Zero point 0.9. If the clearness index is 0.75, so KT is given as 0.75. And the reflection coefficient we denote it as rho, and it is given as 0.1. So what is the overall tilt factor? We have to find the gamma T. So we need to find the overall tilt factor that we denote as gamma T. This is the formula discussed in the big four lectures. So we have to see the expression. So what is the expression we have written before? So just I am telling you here. So we have written this equation. So here you can say that this gamma T is written as, from here we can write gamma T as 1 minus HD upon HA into RD plus HD upon HA into 1 plus cos beta upon 2 plus rho into 1 minus cos beta upon 2. So you need to remember this expression also. So overall tilt factor is 1 minus HD upon HA into RD plus HD into HA into 1 plus cos beta upon 2 plus rho into 1 minus cos beta upon 2. I hope you understand this, how we will got this overall tilt factor. So I am writing down here. So we have to find this overall tilt factor, and tilt factor is 1 minus HD upon HA into this tilt factor RD and this gamma T is overall tilt factor. Plus HD upon HA into 1 plus cos beta upon 2 plus rho into 1 minus cos beta upon 2. So we have to use this expression. So here we are knowing all the values. RD we are knowing, beta we are knowing, rho we are knowing. Rho is what? Rho is the reflection coefficient. we don't know this SD upon HA. So we have seen this one relation more, that is denoted by curve fit relation. So SD upon HA is written like 1 minus 1 upon 1.13 kT. So from here we will find SD upon HA. So SD upon HA will be 1 minus 1.13. kT is given as 0.75. So you will get 0.1525. Now we will put all these values and we will get gamma T. So we are knowing all these values. So 1 minus SD upon HA is 0.1525. RD is 0.95 plus. So HD upon HA is 0.1525 and cos beta is given as 25 degree plus rho is given as 0.1 minus into 1 minus cos beta cos 20 degree upon 2. So you will get gamma T as 0.955. So correct answer is A. So from here, if you do simplification, then you can say that maximum term will come from the first part only. This 1 minus SD upon HA into RD. This is the coming from this direct irradiance, and then we are having diffused, and then we are having reflected. So it is decreased. So I am writing one more line. So first part is 0.8051 and then second one is 0.145 and the last part is 4.68 into 10 to the power minus 3. So if you do sum up, then you will get 0.955. So the correct answer is A. So did you get the answer? No one is typing today. If you are not understanding, then you can also type and you can ask me. If you do more discussion, the concept will be more clear. So let us come to the next problem. So the next problem is man of height 5 feet 11 inches is standing under the sunlight. The length of the shadow of the person on the plain ground is 50 centimeter. So what is the air mass index from the following? So we have discussed to find the air mass for the shadow and object from the shadow and object length. So we are going to use that concept. This is sun. Let us see. Take this is object length and let us take the object length h. And this is the direct radiation from the sun. And then the shadow will be like this. So this is the shadow length. Shadow length is S. This is the theta. So how we'll find the air mass index? So for that, we can write L equal to here this hypotenuse length this hypotenuse length upon object length. So hypotenuse length will be s square plus h square, and object length is h. So it will be root 1 plus s upon h square. So put all these values. So 1 plus s is 50 centimeter. So here s is given as 50 centimeter and object length is given as 5 feet. So 1 feet into 12 inch. So 12, 5 into 12 plus 11. So it will give you 71 inch. Now 1 inch equal to 2.54 centimeter. So 71 into 2.5, so 4 centimeter will give you 180.34 centimeter. So 1 inch equal to 2.54 centimeter. If you don't know this lesson, then you cannot solve the problem. So 50 upon 180.34 into a square. So this will give you 1.077. So it will give you 1.034. So the correct answer is, sorry, it will give you 1.04. The correct answer is B. Anyone got the answer? Can represent this air mass for this problem is AM 1.04. So is there any doubt?
No, sir. No any doubt. Just
Am I
I
audible?
want. Yes, sir. Yes, sir.
Okay, coming to the next problem. So here a Fourier series based approach has been made to estimate the clearness index of a locality for a set of given input. The estimated clearness index is expressed as KTE A1 plus A2 sin tau plus A3 cos tau and AI equal to AI1 plus AI2x plus AI3x square, where I equal to 1 to 3. What is the size of coefficient matrix of unknown variables AI1, AI2 and AI3? So how we will solve this problem? So let us first write all these things. So for this you can refer the class lecture also, but here how the sir has estimated this KT clearness index. So I will writing down the steps, and from the steps you can find this what will size of the coefficient matrix. So here this estimated clearness index is expressed as A1 plus A2 sin tau plus A3 cos tau. So this is the estimated clearness index for a locality. And this coefficients are given as AI is given as AI1 plus AI2x plus AI3x square. So now we will put for A1, A2 and A3. So A1 will be A11 plus A12x plus A13x square. Now similarly A2 will written as A21 plus A21x plus A23x square, and A3 will be written as A31 plus A32 plus A33x square. Therefore, this KTE can be written as, just we substitute all these values here. So it is written as A1 1 plus A1 2x plus A1 3x square plus A21 plus A21x plus, sorry, this will be A22 A23x square into sin tau plus A31 A32x plus A32x square into cos tau. So this is the estimated clearness index for a locality. Now we have to find the coefficient matrix of unknown variables. So how we can find? So for this we will write the error value first. So error value is written as this actual value minus estimated value. So E equal to KT minus KTE. And then we are using the least square error. So J equal to written as I summation EI square. So it is I summation of KT minus KT EI square. So we have to minimize this function. So we have to minimize this function least square error to obtain best estimate KTE. So for that, how we can proceed further? So we have to set this function with respect to the coefficient. So set del j upon del 11 del j upon a12 del j upon a13 del j upon a21 del j upon del a22 del j upon del a23 del j upon a31 del j upon del a32 and del j upon a33 to 0 individually. So if you do simplification, if you do partial derivative of this least square error with respect to all the coefficient, then we are having so you do the partial derivative of this function with respect to all the coefficient, then we will get how much equation? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we will get 9 equations. We will get 9 equations. And how many unknowns are there? There are 9 unknowns. A11, A12, A13, A21, A22, A23, A31, A32, and A33. So there are 9 unknowns. And if you write in the form of matrix, then it will become 9 cross 9 matrix. So the size of coefficient matrix of unknown variables will be 9 cross 9. So C is the correct answer. If you know the answer, you can type on chat box. Otherwise, how I will know that you are getting the correct answer or not? The participants are less today. Rajesh, Ramesh, Garg, and Neeraj, Rajnikant, Deepak, and Salini.
Due to the festival, sir.
Which
Maybe.
festival today?
Today not. Tomorrow is the Rakhi festival. So
Yeah.
that's why.
Yeah, this is the typical scenario of any NPTEL lecture, because I have taken this is the 4th time I am taking tutorial session. So all the time people are very motivated at the starting, at the beginning, and they are very very curious about the course, and they are understanding each and everything better. But day by as the days past, then at the end there are very less people who are always they are just keep on learning. I don't think it will increase. So day by day, these people will be constant only. Those who are sincere, they are only be present after 2 or 3 session. So let us come to the next problem. And I expect the answer from you.
Sir, before going to this question, just I want to one suggestion with you. Actually, in this course, there are lots of derivatives and lots of big formula. So how
Yeah.
we can remember all the things?
So
We will
that is,
forget
yeah.
most of the time.
Yeah, that is the thing. But more problem is solved, the more you will get easily to remember. But in the last tutorial session, we all I think all the PMRFTS will take one revision session. So you can attend that session, and we can just quickly revise all the important things for the exam. Because before the exam, we have to just keep one short note. You cannot go and revise all the notes, read all the things before exam. If we are having short notes, those things that are difficult to remember, we have to keep in mind. And this is the only, I think, this tutorial number 3 and tutorial 4. In this session only, there are more expression, mathematical expression and that are empirical formulas. So it is really somehow a little bit difficult to remember. But most of the things, if you see, if you are knowing the concept, then you can easily, if there are options given for that problem, then you can also just suppose what should be the answer. Because for declination angle, you know that what is the range for declination angle. If the range goes beyond that declination angle, then it will not correct answer. But for numerical answer type, you have to remember the equations very carefully. But if the question come from this total 3 and 4 and the options are given, then you can easily get the answer without solving the problem. Sometimes if the answers are not given in a short range, because you know the what should be the hour angle, sunrise hour angle and day of length, they may put some how you can say, they may put some value that are beyond the range. So it is just right now we focus on the concept, and at the end you can have short notes and you can just take a look before the exam. So I just suggest that just focus on the concept and learn each and everything, and at the end you just take care of all the expression, and we will provide at the end in the last session tutorial 12, because you can see that this is one session beforehand. So in last tutorial session we are going to have we are going to provide the revision session, or we can take one other special session also. So don't worry about that. Okay, all right. So let us come to this problem 6. So which of the following is a significant factor for the attenuation of spectral irradiance in the infrared region seen as notches in the figure? This is one of the easy problem, and sir has discussed it in the lecture. Can anyone tell the answer? Yes. Ramesh, you know the answer for this problem? So the correct answer is not ozone is not the correct answer. Yes, Rajnikant, you are right. This water vapor. The correct answer is water vapor. So these notches in this infrared region due to water vapor. Another factors also, but significant factor is due to water vapor. D is the correct answer. Now come to the next problem. The next problem is that the direct optical path length of the insulation through the atmosphere defined by the air mass coefficient at the sea level is 1.5 m 1.5. What will the zenith angle found by zenith axis and the insulation line for the IISc Bangalore, Gulmohar Bengaluru, Karnataka, India, which is located at a certain height from sea level? Consider the pressure measured at a given location is 99 and 20 millibar. So this we have also provided the equation for solving this problem. So this AM 1.5 is given. So take it as AML1, AML is given. So this is given at pressure equal to 1000 millibar at a standard pressure at sea level. So now we have to find the AML star and that pressure level is given as, that we can write P star, that is given as 920 millibar. So we know one relation, this L star equal to L equal to P upon P naught. So this is P naught. L star we need to find. So L star equal to P upon P naught, and L is given as 1.5. Okay, here I am doing mistake. Sorry. So this is P only. So P is 920 and it is P naught is 1000. L star corresponds to at pressure 920 millibar and L corresponds to a standard pressure at sea level 1000 millibar. So L star you will get 1.38. So we know this L star how to get the angle, how to get the zenith angle. It is denoted as 1 upon cos theta z. So cos theta z you will get 0.7246. So theta z will be 43.56 degree. C is the correct answer. So what is the pressure at sea level? Pressure at sea level is 4,000 millibar. So we have used this. So you can find the zenith angle if you are given the pressure at a place other than the sea level and you are knowing the air mass index for the sea level. Okay, all right. So let us move to the next problem. The next problem is quite easier one. A second class pyranometer LP Pyra 03 AV is provided with a split level, a 4-pole plug having a 0 to 10 volt signal output connected to DMM and a power supply is shown in the figure. To read the signal, the load resistance kept greater than equal to 100 kilo ohm. The pyranometer is mounted on the terrace of the building where no obstruction exceeds the horizontal plane. The instrument output voltage measured with the DMM digital multimeter is 4.8 volt. What will the display on the pyranometer in watt per meter square? Assume the
Sir,
instrument.
maybe your screen has been freeze.
You are not seeing this question number 8.
Yeah, right now we are able to see.
Okay. I think there is a network problem from my side. So as per the data sheet of LP Pyra 03AB, when the DMM displays 10 volt, the irradiance measured is 2000 watt per meter square. So here a parameter is given. So here this is power supply is going to this parameter on this side, and here this is digital multimeter DMM. From where we are taking measurement. And this load resistance is kept greater than 100 kilo ohm. So this load resistance so it is placed on the terrace of building where no obstruction exceeds the horizontal plane, and this instrument output voltage measured with digital is 4.8 volt. So it is measuring 4.8 volt. What will the display in parameter in watt per meter square? And from the data sheet, they are given that for this irradiance level of 2000 watt per meter square, this digital multimeter displays 10 volt. So what will be this display parameter in watt per meter square for display of 4 volt, 4.8 volt? So this is quite easy problem, and all the things they are given in the problem, it's just to make the problem lengthy, and there is no use of that. So it is just unitary method you have to apply. From the data sheet, it is given that 10 volt corresponds to 2000 watt per meter square. Now, since 10 volt corresponds to 2000 watt per meter square, so 4.8 volt will corresponds to what is the radiance level. So to 4.8 volt will corresponds to 2000 upon 10 into 4.8 watt per meter square. So it will give you 960 watt per meter square. So this is the answer for the problem. And this is a numerical answer type. So you have to type the answer is 960 watt per meter square. Now coming to the next problem. So this problem is directly given from the lecture slide. So if you are gone through the lectures, then you are easily able to give the answer. So this problem says that the curve fit model of the cleanliness index for India based on the data of 12 cities I discussed in the lecture will give very good accuracy of the estimated clean index when x equal to, and here this we have to consider the function of latitude only, and x is same I described in lecture. So this is the snap from the lecture. So here we have this expected cleanliness index is considered like this function, this curve fit model. So a1 plus a2 sin delta, a3 sin 2 delta, a4 sin 3 delta, a5 cos delta, a6 cos 2 delta, a7 cos 3 delta, and where tau is periodic type, and this is delta is 2 pi into n minus 80 upon 365, and these coefficients are denoted as ai1, ai2x, ai3x square plus ai4w plus ai5w square. And this here you can see that x is equal to 5 minus 35 degree. and W is into G1 plus G2 sine tau, G3 sine 2 tau, G4 sine 3 tau, and so on. And here Gi is Gi1 plus Gi2x plus Gi3 plus square. So from this class lecture, you can see that this x will be function of latitude and the relation is pi minus 35 degree. C is the correct answer. Now coming to the last problem. Here for the curve fitting, and this type of problem is given in the class also, in the assignment 4 also. So just carefully see this problem. You will be able to solve the assignment 4 problem also. So for the curve fitting for the clearness index, consider the. Are you able to see the problem number 10?
Yes, sir.
Okay. Consider the following data: KT equal to 0.6.7, B equal to 1 2, C equal to pi, tau equal to pi by 2. This is the range given for each problem: pi by 2, 3 pi by 2, and KT is A1 sine tau, A1 equal to A1 plus A2x, where x is equal to B. And then we have to find A1. So this looks very complicated one, but if you see the solution, it is very easy. So we will start from the range they are given. So tau is given as from pi by 2 to 3 pi by 2. So here this tau comes under the sine function. So first find sine pi by 2. So it will be 1, and sine 3 pi by 2, it is minus 1. And this KT is the function of A1 into sine tau. And A1 is given by this relation. Now this is also given that this, if tau is pi by 2, this KT is coming as 0.6. So we will put this value. So at tau equal to pi by 2, this KT equal to 0.6. So this will give 0.6 equal to this sine pi by 2 is 1. So 0.6 equal to A1, and at tau equal to 3 pi by 2, this KT equal to 0.7. So this is 0.7 equal to minus A1. So we got for tau equal pi by 2, this A1 is equal to 0.6, and for tau equal 3 by 2, this A1 is equal to minus 0.7. So now A1 equal to A1 plus A2x, and this x is equal to B. So we can write A1 plus A2 into B. And this B range is also provided. B range is also provided. So we will use the boundary condition only. So at tau equal to pi by 2, A1 equal to 0.6, and B is given as 1. So therefore, it will become, you will put all this value here. So this will be A1 will be 0.6 and A1 plus A2. So B A1 plus A2B, B is 1. So 0.6 is equal to A1 plus A2. So take it as equation number 1. And now at tau equal to 3 pi by 2, this A1 equal to minus 0.7 and B equal to 2. So we will get 0.7 equal to 7 minus A1 plus 2A2. So this is the second relation. So from first and second, first and second, you will get A1 as minus 1.3 and A2 as 1.9. So we can write A1 equal to A1 plus A2 into B, and B is X. So A1 equal to A1 become 1.9 and B1 got A2 we got minus 1.3. A1 is 1.9 minus 1.3 X. The correct answer for this problem is A. So I will add the PDF of this today's session, so that it will be more helpful to you. But I will not discuss here because it will take more time. So I will add some more problems for today's session, and you can go to the PDF of slides where I will upload tomorrow. So any
Sir,
doubt?
where are you uploading these slides?
We just can do for 29. Okay.
Sir, are you able to hear me?
Yes, Ramesh. So you can go to Swam portal.
Okay.
You can go to Swam portal. Swam portal. There you can find the. In Swam portal, you are you able to access the recordings?
Yes. Yes,
So
sir.
there I will upload. So here,
Okay, sir. Thank you, sir.
Okay. Any other thing you want to ask?
No, sir. Thank you.
Okay. Okay. Take care. Good night, and we will meet at the same time on the next Sunday.
Good night, sir. Thank you.
Welcome.